Hi everyone. Good morning, good afternoon, good evening, or even good night. So I think this could be the final recording of my academic life here. So I'm just going to go for it. And the reason I'm doing this, it's really for myself, and it will not appear in any lesson. I just want to have this recorded so I can access it myself. Because most people know I won't use the phrase. I think too much of myself, maybe. Anyway, let's go for it. So, the wee topic I picked here is square root approximation. Because it's something that I've been interested for a while here, and it's something square roots and cube roots, or squares and cubes, I've always been interested in the mental arithmetic. So this is what this is all about. And this only came to me, I don't know, maybe 12 months ago. And it kind of came out the blue for me. So what I'm saying here, if n is a positive integer, and I'm actually going to qualify that, it can actually be irrational. But usually you would just deal with integers, because folk will say, oh, what's the square root of 36? What's the square root of 64? What's the square root of 50? They don't usually say to you, what's the square root of 12.25? Things like that there. No, they don't usually say that. Even though that's 3.5. That's another thing. So, it's too late to change this lesson anyway. So, but it's your target is not a perfect square. So, like I said, there's a crude approximation. So if we go for the closest value, which is a square, we can use this formula here. Square root of n is approximately equal. That's what your approximately equal, your double tilde there. So the target plus the nearest square times 2 times the square root of the perfect square. Right, okay. So that's what I'm saying. Target number, closest perfect square. And so I'm saying here that this might not be original. It probably isn't original. But that's not my motivation for producing this. I don't think I've seen a derivation of this before in my life. My short life. And I have searched for it, you know, after I came up with my version of it. I'm sure that's like a student coming up to you saying, do you know a half plus a half equals 2 halves and is equal to 1? Did you know that? But anyway, so this is my moment. So, like I said, it did come out, came to me out of the blue. Honestly. Aye, and yous are very judgmental people, whoever's going to watch this. if anybody watches this at all, because this battery might run out. So I'll let you be the judge and jury and executioner. So here's my kind of derivation. Thomas, that's my weirdo name that I've used over many years. That's fine. My handle, if you want to call it that. Right. So I'm going to let the target number I'm looking for be a positive fraction. Okay. Remember the rationals, positive rationals, and it's not a perfect square within the rationals, positive rationals. But S, its partner in crime here, that's going to be a perfect square within the rationals. That's what we want. So what I mean by that, a perfect square, I mean like 25 is a perfect square because square root of 25, positive square root. Just to let you know, technically square roots are always positive. Doesn't matter what anybody else has told you. There are certain circumstances where you have to take a positive negative value, but if you said take the square root of a value, it's a positive answer you're looking for. So the square root of 49 is 7. The square root of 4 over 9 is 2 over 3. Positive, positive. Okay, sorry, I had to get that off my chest. Right, so here's the square root of the target number. Right, so it's the square root of n plus 0. Why doesn't choose 0? Because 0 plays a massive role in this. Because it's disguised as s minus s, because we need to introduce s here. Just a little bit of rearrangement there. And a little bit of factorising here. If in doubt, go back and multiply out that out there, and see you'll get the fourth line, the one above. So let's continue. I can't do this all on one page because you'll be scrolling. Right, so I've got rid of all the old radical symbols and just introduce, because it's technically we assume these are square roots, which is the index of a half. So I've done that. And it's actually that expression that I'm interested in here. It's quite kind of complicated, but we're going to uncomplicate it. Right, let's take this then. And I'm going to make a substitution. See this, all this stuff here, it's too complicated, so I'm just going to pop an X in there. It's like putting a tic-tac in. So I'll just make it equal to that here. So 1 plus x to something, that's like 1 plus x to the n, and which supposedly is binomial by 1, 2, 1, 2, 1 by 2 terms by binomial 2 terms. But you know that. So, and the binomial expansion of that there is 1 plus that there, plus that there, plus that there. You either know it or you don't. Right. So if you're actually watching that, then you might have a wee bit of background. Okay? And you're actually my target audience. And if this finds itself, it will find itself on YouTube anyway, then hopefully you'll be able to figure it out. So, but what I'm looking at here is, see for x, I want x to be really small. X is very, very much less than 1. And see that there? The modulus of x, the magnitude of x, the size of x. That's what we're talking about here. Regardless of being positive and negative, it's very much less than 1. And you can debate what is very, very much less than 1. We can debate about that. Or you can. So that means here 1 plus x to the n is approximately equal to just the first two terms. So that's what I'm going to be using here in my derivation. And like I'm saying, go and do a wee bit of research there. And you might find that, and you might find that. Don't always trust the internet. So, let's go for it. So according to that, we'll have that there. It's a lot simpler, isn't it? So, let's go back to that expression that I was highlighting earlier. And let's go back, because I put x back in, right? So, you see, x has went back in there, right? So let's go back to derivation, as I'm saying here. Put that in there. Okay. So what's happened here between this line and the next line? I've got 1 and then I've got a kind of fraction here, but I want to combine these, so I need to express 1 in relation to this denominator here. So if I express 1 as something divided by itself, probably pick 2s divided by 2s. Okay, so I've got a common denominator. Right, so that's what I've done there, and then I can just bring these together. Okay, so that's all I've done there. Then the 2s, take away the s, they'll be able to combine to give me that there. And so that's what I've got. And s to the half, when I multiply out the bracket, the s to the half basically interacts with the s in the bottom, which is s to the 1. S to the half becomes s to the negative half. And that's what I end up there. Have a wee think about it. And then I've just exchanged the rational index for the old-fashioned radical sign, because we like that. So that means that our approximation for the square root of our target number is just equal to the square, is equal to the target number plus its a square, a perfect square, over the, all divided by 2 times the root of that perfect square. So that's the method. So if you like the derivation, good, bad, or you can dismiss it out of hand. But at least I'm having a go, folks. Okay, I'm having a go. Right, let's see. Does it work? Let's pick a wee example here. 711. Oh, 711. Is that prime? No, it's no, because 7 and 1 is 9, so it's divisible by 9. Okay. So it's no prime, it doesn't, but it's not a square. But I'm going to use approximation here, and that's my target, 711. The closest kind of natural number square is 729, 27 squared. So I'm going to use 27 here. So we just put them in, put everything in position. So 711, 729 on the bottom, 2 times the root of 729, so that's 2 times 27 on the bottom, 54. Well, I get that there. 1440 over 54. I can see that both are divisible by 9. So I've done that, and then I can see 160 over 6, both are divisible by 2. 8 over 3, yep, I've done that. And 8 divided by 3, I'll express that as a fraction. It's not quite 27. and a wee bit less, 26 2/3. But I want to use like decimals, so I'll just put it in the 3 decimal places. I've done that for a reason. Okay. So now, using the calculator, I get 26.665. So that's why I went for 3 decimal places here, because we were only one out in the third decimal position. Right. So that was actually okay. I was quite pleased with that. A lot of times I wouldn't use the calculator because the motivation for me for this was to use mental arithmetic. So that's what I'm going to do this in. Square root of 133. 133, is that a square number? Obviously it's not going to be if I'm using it. It's actually 7 times 19. But anyway. So but it lies between two kind of natural squares, is 11 squared and 12 squared, 121 and 144. And it's kind of in between them. But so 11 and 12, they're quite far away for the target route I'm looking for. So I'm going to look for 11. I'm going to use 11.5 because 11.5 squared is 132.25. Right. Okay. And I just said that's almost sitting on top of the target, 133. So this is just showing you. So 121 is quite far away from the target, and 144. That's pretty far away from the target. If I take the 133.25, that's almost bang on the target. So I should get a better approximation. So that's what I'm saying here. The closer you can get a rational square to the target, the better. Because we want to get as close to that bullseye as possible. And that's just slightly, just summing it up for you there. Just remember, with these videos, you can always pause, turn it off, or pause and rewind, or phone a friend. Right, so here, this is the target, 133, and that's what it says, 132.25. That's what we're going for, that's the closest rational square. Because the square root of that is 1.5, okay? And because the target is bigger than 132.25, our root is going to be bigger than the root of 132.25. So our approximation should be just over 11.5, just a wee bit over, but not by much. So let's just go and use the derived formula from earlier, where the target is 133 and the perfect square is 132.25. Let's go. Let's just put more numbers here. So I've got 265.25 over 23, and I always like to do this by hand or by brain. So 23 into that, 23 into 26, right? So just that's so it was 23 into 26, and that's how I got the 1 there. Okay. Next, so I did 1 times 23 to get 23, and I'm going to find the difference between these. 26 to get 23 is 3, and then I need to bring this number down here. This is long division. Okay, so then I say, right, okay, how many 23s on 25? Oh, not a lot. How many whole lots of 23 actually? So I think that's 1. Okay, so then so I do 1 times 23 to get 23, find the difference between 35 and 23, which is 12. Okay, so then what I do next is I bring down the next number, bring that down there, so I've got 1, 2, 2, then I say, well, how many times does 23 get to 1, 2, 2? So you're doing your 23 times table there. Okay, so you do 23, 46, 69, 92, 115, was it? Actually, it goes into 5 times, so it is 115. Right, so then I'm running out of space here, so it's shorter here. So again, I find the difference between name, 7, I've no numbers left up top, so I just have to bring it on. In fact, I do. I've got a 5, bring 5 down, and then I say, well, how many times is 23 into 75? So I say 23, 46, 69. Oh, so is that 3 times? It is. Right. And we just keep going. So 3 times 23 is 69. Find the difference. 6. No more numbers left. So I need to bring down a 0. And so 23 goes into that twice, because 3 times 2 is 46, which isn't greater than 69. So I think I'm going to leave it there. I could just go in ad infinitum. Right. So 3 decimal places, I think that's good here. So if you don't like doing long division, you can always use your calculator. So that was the approximation value. This is the square root value with a calculator. And you can just check how close they are together. So 11.532, 11.532. We've got a 6 here, but we've got a 5. Oh, so see if that 6 was rounded up to a 6 if I rounded it. So actually to 4 decimal places they're correct. So I'm actually quite happy with this here. And I'm not happy. I'm out in my back garden and I'm rooting about down there checking out my square roots. Okay. Like I said, folks, earlier, this wee video is for my benefit. But if any of you appreciate it, then that's fine, but I'll never hear about it. So, you all take care. Bye.